Hey there, and welcome to the Sleepless Scientist. Tonight we embark on a journey not through space, but through scale itself. Imagine, if you will, the universe unfolding before us, from the tiniest particles that whisper into existence to the grandest structures that echo across eternity. We'll explore the quiet patience of discovery, the moments when a single observation reshaped our understanding of everything. It's a story of human curiosity, pushing the boundaries of what we thought possible, one careful measurement at a time. Before we dive into the cosmic depths, if you enjoy these quiet explorations, please take a moment to like this video and subscribe to the channel. It helps us continue these journeys together. Now, let's begin our gentle descent into the very fabric of reality. Our story begins at the absolute smallest scale, a place where our everyday senses fail us entirely. Picture, if you can, a single atom, not a solid miniature ball as once thought, but a cloud of probability, mostly empty space. Within this tiny realm, a nucleus holds court, orbited by electrons. The distances between these particles relative to their size are staggering. It's a miniature solar system, a universe within itself, silent and profound. The very air we breathe, the chair you might be sitting on, the screen you're looking at, all are composed of these fundamental building blocks. Each atom, a tiny whisper of existence, contributes to the symphony of matter. For centuries, the atom was a philosophical concept, an unseeable limit. It was only through patient experimentation and deduction, not direct observation, that scientists began to uncover its true nature. This realization that the seemingly solid world is mostly void at its core was a profound shift. It taught us that reality often hides its deepest truths beneath layers of apparent simplicity. Now let's step up in scale. From the atom, let's consider something familiar, the human hand. Intricate, capable, yet still a collection of countless atoms working in concert. Our own bodies are vast universes to an atom, but how do we, in turn, compare to our home, Earth, a tiny speck upon its surface, a fleeting moment in its geological timeline? The Earth itself, a magnificent blue marble, spins through space. Its immense sphere, with oceans and continents, dwarfs anything we can build. Its scale is difficult to grasp without stepping away from it. For much of human history, the Earth was considered the center, the largest and most important body. This geocentric view, while comforting, limited our understanding of true cosmic scale. The intellectual challenge of grasping magnitudes beyond human experience has always driven us. How could we measure something so big or so small that it defied our direct senses? Ancient civilizations looked to the stars, charting their movements, yet their understanding of distance was largely conceptual, tied to deities and fate rather than physical measurement. The cosmos was a dome, a sphere of fixed stars with wandering planets moving in complex but ultimately local patterns. This was the prevailing model for millennia. It was a coherent system, one that explained the observed movements, but it placed humanity at a unique, central position, preventing a true appreciation of universal scale. The very act of looking up, however, sparked an unquenchable curiosity. What lay beyond the visible? What were those distant pinpricks of light truly made of? This curiosity began to be truly challenged not by new philosophy, but by new technology. A simple lens, ground with precision, would soon shatter ancient cosmologies. In the early 17th century, a new instrument emerged, the telescope. It wasn't just a magnifier, it was a window to the universe, extending human sight far beyond its natural limits. Galileo Galilei, with his improved telescope, turned his gaze skyward. What he saw began to unravel centuries of accepted wisdom, piece by painstaking piece. His observations of the moon were among the first. No longer a perfect, smooth sphere, it was a rugged world, scarred with craters and mountains, much like Earth itself. This observation suggested that celestial bodies were not fundamentally different from our own planet, a radical idea at the time. The heavens were not perfect and unchanging. Then came Jupiter. Through his rudimentary telescope, Galileo saw not one but 4 small stars orbiting the giant planet. These were Jupiter's moons, a mini-solar system in action. This was a profound discovery. If moons orbited Jupiter, then not everything orbited Earth. The geocentric model, with Earth at the absolute center of all celestial motion, began to crumble. Galileo's observations provided tangible evidence that the cosmos was a much more dynamic and complex place than previously imagined. It was a universe of relative motion and multiple centers. The challenge now was to understand the true distances involved. If Earth was not the center, how far away were these other worlds? How vast was the solar system? Early attempts to measure these distances were ingenious, using geometry and the changing positions of planets. They hinted at scales far beyond human comprehension. The shift from Earth as the universe's anchor to a mere planet orbiting a star was a humbling, yet liberating, realization. Our place was not unique in its centrality, but unique in its existence. This conceptual leap allowed scientists to begin to truly map our solar system, understanding the vast empty spaces between planets and the sun's immense gravitational pull. The quiet observations of these early astronomers, though met with resistance, laid the foundation for a cosmic perspective that continues to expand with every passing century. But the solar system, vast as it is merely our cosmic backyard. Beyond it, the stars, once thought to be fixed points on a celestial sphere, revealed themselves as distant suns. How far away are they? To grasp these distances, we needed a new unit of measurement, one that reflected the immense scale. Enter the light year. A light year is the distance light travels in 1 Earth year, nearly 6 trillion miles. The nearest star to our Sun, Proxima Centauri, is over 4 light-years away. This means we see Proxima Centauri not as it is now, but as it was 4 years ago. Looking into deep space is like looking back in time, a profound connection to the past. The very idea of light taking years, even thousands of years, to reach us from distant stars stretched the human imagination to its breaking point. Yet it was a fundamental truth. As telescopes grew more powerful, the hazy patches of light known as nebulae became objects of intense study. Were they gas clouds within our own galaxy or something else entirely? The great debate of the early 20th century centered on this question. Were these nebulae island universes vast collections of stars, much like our own Milky Way, but incredibly distant? Edwin Hubble, using the powerful Hooker telescope, provided the definitive answer. He identified individual stars within the Andromeda Nebula, and critically, a type of variable star called a Cepheids. By measuring the brightness of these Cepheids, Hubble could calculate their immense distances. Andromeda was not a nebula within our galaxy, it was a galaxy itself, millions of light-years away. This discovery shattered the perception of the Milky Way as the entire universe. It revealed a cosmos teeming with countless island universes, each a galaxy, each a home to billions of stars. Our journey into scale had truly begun. Our last journey revealed a cosmos teeming with galaxies, each an island universe of unimaginable scale. Now, let us narrow our gaze from the grand galactic tapestry to the individual stars that compose them, those distant suns that once seemed merely points of light. For centuries, the stars were enigmas. What made them burn so brightly for so long? What was their true nature, beyond being distant, luminous objects? This question quietly puzzled scientists as they mapped the heavens. In the early 20th century, a new tool, spectroscopy, began to unlock these secrets. By splitting starlight into its constituent colors, scientists could read the chemical fingerprints embedded within. Each element, when heated, emits light at specific wavelengths, creating a unique barcode. This allowed researchers to determine what distant stars were made of, even without touching them. The initial assumption was that stars would have a chemical composition similar to Earth's, rich in heavy elements. It seemed logical; our world was made of what was available. But the data from stellar spectra told a different story. The patterns were not matching expectations. There was a subtle, persistent discrepancy that hinted at something profound. A young British astronomer, Cecilia Payne, working at Harvard College Observatory in the 1920s, delved into this spectral puzzle with a quiet determination. She meticulously analyzed thousands of stellar spectra, applying the new quantum physics to understand how atoms absorbed and emitted light at different temperatures and pressures. Her calculations led to a startling conclusion: the Sun, and by extension all stars, were not like Earth at all. They were overwhelmingly composed of the two lightest elements, hydrogen and helium. This finding was so radical that her thesis advisor initially discouraged her from publishing it. It challenged the prevailing wisdom, suggesting a cosmic composition vastly different from our own planet. Yet Payne persisted. Her meticulous work was undeniable. Her conclusion that hydrogen was 1,000,000 times more abundant than previously thought gradually gained acceptance. It was a quiet revolution, revealing that the universe's most common ingredients were also its simplest. This discovery was a cornerstone for understanding how stars truly functioned. If stars were mostly hydrogen and helium, then their energy source could not be simple combustion. A different, more powerful process had to be at play to sustain their immense luminosity for billions of years. The answer lay in the heart of the atom itself, in the very forces that bound its nucleus. It was a process of cosmic alchemy, far grander than any alchemist's dream. Deep within a star's core, under unimaginable pressure and searing temperatures, hydrogen atoms are forced together. This is nuclear fusion, the engine of the stars. In this fiery crucible, 4 hydrogen nuclei combine to form one helium nucleus. A tiny amount of mass is lost in this transformation, converted directly into a tremendous burst of energy. This energy radiates outwards, pushing against the star's immense gravity, creating a delicate balance that allows stars like our Sun to shine steadily for eons. But stars are not static. As they consume their hydrogen fuel, their cores change. The helium accumulates and the star begins a new phase of its life. In more massive stars, once the hydrogen is depleted, the core contracts further, heating to even more extreme temperatures. This allows helium nuclei to fuse. 3 helium nuclei can combine to form a carbon nucleus. Then, carbon can fuse with helium to create oxygen. The stellar core becomes a cosmic forge, building heavier elements step by step. This process, known as stellar nucleosynthesis, explains the origin of most of the elements in the universe, up to iron. Each element is a byproduct of a star's life cycle. The journey from hydrogen to helium, then to carbon, oxygen, neon, magnesium, silicon, and finally iron, is a slow, patient dance of atomic nuclei within the star's heart. Each stage requires higher temperatures and pressures, burning through fuel at an increasingly rapid pace. The star transforms itself from within, layer by layer. But iron is a unique element. Fusing iron nuclei together actually consumes energy rather than releasing it. This marks a critical turning point for a massive star. Once a star's core is mostly iron, the outward pressure from fusion ceases. Gravity, which has been held in check for millions of years, suddenly wins the battle. The core collapses in a fraction of a second, creating an unimaginable shockwave. This is the moment of cosmic drama, a supernova. In that cataclysmic explosion, temperatures and pressures briefly reach levels never before seen. This fleeting, intense environment allows for the creation of elements heavier than iron. Gold, silver, uranium, these precious and heavy elements, rare on Earth, are forged in the final, violent moments of a dying massive star. They are truly stardust, born of cosmic death. The supernova explosion then blasts these newly forged elements, along with much of the star's original material, out into the vast emptiness of space. They become part of the interstellar medium. These enriched clouds of gas and dust, infused with the remnants of long-dead stars, are the nurseries for future generations. The cycle of cosmic life and death begins anew. Over vast stretches of time, gravity draws these scattered particles together. New stars ignite, and around them, planets form from the same enriched material. Our own solar system, including Earth, formed from such a cloud. The elements that make up our planet, and indeed ourselves, were once locked within the hearts of ancient stars. The carbon in our bones, the oxygen we breathe, the iron in our blood, all were forged in the fiery furnaces of stars that lived and died billions of years ago. We are, quite literally, stardust. A profound realization that connects every living thing on Earth to the grand, violent, and creative processes of the cosmos. The patient work of astronomers, spectroscopists, and physicists, from Cecilia Payne to those who followed, gradually pieced together this magnificent cosmic narrative. It was a story told not in words, but in the subtle shifts of light, in the echoes of ancient explosions, and in the very composition of the world around us. The universe, we learned, is a vast, interconnected cycle of creation and destruction, where the death of one star seeds the birth of others, and even of worlds. Our understanding of this cosmic alchemy deepened our appreciation for the transient yet eternal nature of matter, and our own small, precious place within it. The elements that form our bodies and our planet are not unique, but are part of a universal heritage, constantly recycled and reborn across the eons. As we trace the journey of these elements, from stellar cores to the dust of nascent planets, a new question emerges. How did these enriched cosmic ingredients eventually come together to form the worlds we now know? That, perhaps, is a story for another quiet contemplation. Our previous journey concluded with the elements, forged in stellar furnaces, coalescing into new stars and nascent planets. Yet, these individual stars and their systems are not isolated. They are born within immense clouds of gas and dust, which themselves are components of far grander structures. For centuries, astronomers observed faint, fuzzy patches of light in the night sky, labeling them nebulae. Their true nature remained a profound mystery. Were they merely gas clouds within our own Milky Way, or something far more significant? The question of these nebulae's distances was paramount. If they were truly external to our galaxy, they must be unimaginably far away, making them island universes of their own, each a collection of billions of stars. In the early 20th century, a new generation of telescopes offered unprecedented clarity. Among them, the Hooker telescope at Mount Wilson Observatory in California, a monumental instrument for its time, stood ready to probe the cosmic depths. It was here that Edwin Hubble, with patient dedication, began to systematically photograph these mysterious nebulae. His goal was to resolve individual stars within them, a task that demanded exceptional observational skill and tireless hours at the eyepiece. In 1923, focusing on the Andromeda Nebula, Hubble made a crucial discovery. Among the countless faint points of light, he identified a specific type of star, a Cepheid variable whose brightness pulsated with a regular rhythm. These Cepheids were cosmic lighthouses. Henrietta Swan Leavitt had previously discovered a fundamental relationship. The longer a Cepheid's pulsation period, the brighter its intrinsic luminosity. This meant they could be used as standard candles to measure vast distances. By comparing the observed brightness of the Andromeda Cepheids to their known intrinsic luminosity, Hubble could calculate their distance. The numbers that emerged were staggering, far exceeding the estimated size of the Milky Way. Andromeda was not a cloud within our galaxy. It was a galaxy itself, a sprawling collection of billions of stars located millions of light-years away. This single observation reshaped our understanding of the universe's true scale. The universe was no longer confined to our Milky Way. It was a vast ocean, teeming with countless island universes, each a galaxy, each a home to its own stellar populations. Our journey into scale had truly begun, revealing a cosmos far grander than imagined. Once we understood the existence of other galaxies, the next question arose: how do they behave? Are they static, isolated entities, or do they interact with one another across the cosmic expanse? Observations soon revealed that galaxies are far from isolated. Gravity, the same force that pulls planets around stars, also draws galaxies towards each other, leading to intricate cosmic interactions. Sometimes these interactions are gentle, a slow gravitational dance that distorts their shapes, pulling long tidal tails of stars and gas into the void. At other times, they are grand collisions spread over hundreds of millions of years. These galactic mergers are not destructive in the way we might imagine. Stars rarely collide, but the gas and dust clouds within them are compressed, igniting bursts of new star formation, fundamentally reshaping the galaxies involved. Over cosmic timescales, these mergers are a primary driver of galactic evolution, transforming smaller spirals into larger, often elliptical, galaxies. Our own Milky Way is destined for such a merger with Andromeda in billions of years. But galaxies do not merely interact in pairs. They gather into larger collections, drawn together by gravity, forming groups and immense clusters. Our Milky Way is part of the local group, a modest collection of dozens of galaxies. These galaxy clusters are some of the most massive structures in the universe, containing hundreds or even thousands of galaxies, bound together by their collective gravitational pull. Mapping these clusters became a new frontier in cosmology. Scientists used redshift measurements to determine distances and velocities, slowly piecing together a three-dimensional view of the universe's large-scale structure. The space within these clusters is not entirely empty. It is permeated by extremely hot, diffuse gas, invisible to optical telescopes but glowing brightly in X-rays, providing further evidence of the cluster's immense mass. The sheer scale of these clusters is difficult to comprehend. Each point of light in such an image is not a star, but an entire galaxy, each containing billions of stars, all held within a cosmic embrace. But the organization of matter did not stop at clusters. As surveys grew larger, covering ever greater swaths of the cosmos, an even more profound pattern began to emerge. Galaxy clusters themselves are not randomly scattered. They congregate into even grander formations known as superclusters, the largest gravitationally bound structures in the observable universe. These superclusters, however, are not isolated islands. They appear to be interconnected, forming a vast, intricate network that stretches across billions of light-years. This is the cosmic web. Imagine a colossal neural network or a sponge-like structure. Galaxies and clusters are concentrated along long, luminous filaments, while immense, nearly empty regions called cosmic voids lie between them. The mapping of this cosmic web has been a monumental undertaking. requiring decades of observations from ground-based telescopes and space observatories, meticulously charting the positions of millions of galaxies. Gravity, the fundamental force that shaped stars and planets, is also the sculptor of this grand cosmic architecture. It drew matter together over billions of years, creating the intricate patterns we observe today. However, as scientists studied the dynamics of galaxies and clusters, a puzzling discrepancy emerged. The visible matter, stars, gas, dust, was simply not enough to account for the observed gravitational effects. Galaxies rotated too quickly at their edges, and clusters held together with far greater cohesion than the visible mass allowed. There had to be an unseen, dominant component of the universe. This led to the concept of dark matter, a mysterious substance that does not emit, absorb, or reflect light, making it invisible to our telescopes. Its presence is inferred solely through its gravitational influence. Dark matter is thought to form the gravitational scaffolding upon which the cosmic web is built. Without it, galaxies would fly apart, and clusters would never have coalesced to form the vast structures we see. It is a silent, unseen architect, guiding the formation and evolution of everything from individual galaxies to the largest patterns in the universe, yet its true nature remains one of science's greatest puzzles. But the universe held yet another, even more startling, secret. For decades, it was assumed that gravity would slow the expansion of the universe after the Big Bang, perhaps even causing it to eventually contract. However, in the late 1990s, observations of distant supernova, a different kind of standard candle, revealed something entirely unexpected. The universe's expansion was not slowing down, it was accelerating. This acceleration implied the existence of a mysterious, repulsive force, pushing galaxies apart on the largest scales. Scientists named this enigma dark energy. Unlike dark matter, which clumps with visible matter, dark energy appears to be a property of space itself, subtly increasing its influence as the universe expands, driving galaxies further apart. Together, dark matter and dark energy constitute about 95% of the universe's total mass energy content. The ordinary matter that makes up stars, planets, and ourselves is merely a small fraction. This revelation has profound implications for the ultimate fate of the cosmos. Dark energy, if its influence continues, suggests a future where galaxies drift ever further apart, eventually becoming isolated in an increasingly cold and empty universe. The discovery of the cosmic web, shaped by the interplay of gravity, dark matter, and dark energy, unveils a universe of immense, interconnected structures, yet still cloaked in profound mystery. We find ourselves within this grand tapestry, a tiny speck on a small planet orbiting an ordinary star, itself part of a filament within a supercluster, all governed by forces we are only just beginning to comprehend. As we ponder our place in this vast, woven universe shaped by unseen forces and unimaginable scales, a new chapter of inquiry beckons. How did this intricate cosmic dance begin, and what does its future hold? That, perhaps, is a story for another quiet contemplation. Our previous journey concluded with the vast, intricate cosmic web, shaped by unseen forces and unimaginable scales. As we peered into the universe's grand architecture, a fundamental question naturally arose. How did this immense structure, and indeed the universe itself, come to be? For much of history, the universe was considered eternal and unchanging, or perhaps created in a static state. This view, though comforting in its permanence, offered no mechanism for the dynamic cosmos we had begun to observe. However, in the early 20th century, a quiet theoretical shift began. A Belgian priest and physicist, Georges Lemaitre, dared to propose a radical idea. The universe had a beginning, a single point from which it expanded. Lemaitre called it the hypothesis of the primeval atom, suggesting that all the universe's matter and energy were once concentrated into an incredibly hot, dense state, which then began to expand. This theoretical spark found observational support in the work of Edwin Hubble, whose earlier discoveries revealed a universe teeming with distant galaxies. But Hubble's observations held another, even more profound secret. By analyzing the light from these galaxies, Hubble noticed a consistent pattern. Almost all of them were moving away from us, and the farther away they were, the faster they receded. This was the observational evidence for an expanding universe. It wasn't that galaxies were moving through space, but rather that space itself was stretching, carrying the galaxies along with it. If the universe was expanding, then running the cosmic clock backward implied a singular point in the past when everything was compressed together. This was the conceptual foundation of what would later be known as the Big Bang. The idea, though revolutionary, was initially met with skepticism. How could such a vast, complex universe arise from a single, fiery beginning? It seemed almost too simple, too dramatic for the calm expanse of space. Yet the expanding universe theory predicted specific remnants from this hot, dense origin. One such prediction was a faint, uniform glow of radiation, a residual heat from the universe's infancy. For the first few 100,000 years after the Big Bang, the universe was too hot for atoms to form. It was a dense, opaque plasma, a cosmic soup of free electrons and atomic nuclei, with light unable to travel freely. As the universe expanded, it cooled. Eventually, after about 380,000 years, the temperature dropped enough for electrons to combine with nuclei, forming the first stable, neutral atoms, primarily hydrogen and helium. This event, known as recombination, made the universe transparent. The photons, previously trapped, were suddenly free to stream across space. This ancient light, stretched and cooled by billions of years of expansion, was predicted to be detectable as microwaves. Meanwhile, in the mid-1960s, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey. Their task was to test a new, highly sensitive horn antenna designed for satellite communication. The antenna was exceptionally quiet, built to minimize all interference. Yet, no matter where they pointed it, they detected a persistent, low-level hiss, an omnipresent background noise that they could not explain. They meticulously checked every possible source of terrestrial interference. They recalibrated equipment, shielded components, and even considered military radar. Nothing worked. The noise persisted, coming uniformly from all directions in the sky. Frustrated, they even suspected the pigeons nesting within the horn antenna. They cleaned out what they famously described as white dielectric material pigeon droppings, hoping to eliminate the interference. Still, the faint, unwavering hiss remained. It was a puzzle that defied all conventional explanations, a subtle anomaly that hinted at something far beyond their immediate research goals. Unbeknownst to them, a team at Princeton University, led by Robert Dicke, was preparing to build an antenna to search for precisely this cosmic microwave background radiation, predicted by the Big Bang theory. A chance phone call connected the two groups. Penzias described their mysterious noise. Dicke immediately realized the profound significance of their accidental discovery. The predicted echo of creation had been found. This serendipitous detection of the cosmic microwave background, CMB, radiation was a watershed moment. It provided compelling observational evidence for the Big Bang theory, transforming it from a hypothesis into the leading cosmological model. The CMB was a snapshot, a fossil light from the universe's infancy, capturing the moment when it first became transparent. Its nearly uniform temperature across the sky indicated a remarkably smooth early universe. The slight temperature variations in the CMB, though tiny, were crucial. They represented the primordial seeds, slight density fluctuations from which all future structures, stars, galaxies, and the cosmic web would eventually grow. After the CMB, the universe entered a period known as the Dark Ages. For hundreds of millions of years, there were no stars to illuminate the cosmos. The universe was filled with neutral hydrogen and helium gas, dark and featureless. During this silent epoch, gravity patiently worked its magic. It slowly drew together the slightly denser regions of gas and dark matter, beginning the long process of cosmic structure formation. Within these growing clumps, the gas became denser and hotter. Eventually, in the deepest gravitational wells, the pressure and temperature became sufficient to ignite nuclear fusion. These were the first stars, often called population Roman III stars. Born from pristine hydrogen and helium, they were likely massive, luminous, and short-lived, burning through their fuel at a furious pace. The birth of these first stars marked the end of the cosmic dark ages. Their intense ultraviolet radiation began to ionize the neutral hydrogen gas that filled the universe, slowly reionizing the cosmos. This period, the epoch of reionization, was a cosmic dawn. As more stars formed and coalesced into the first small galaxies, light gradually flooded the universe, transforming its opaque, dark state into the transparent, star-filled expanse we know today. These earliest galaxies were not the grand spirals and ellipticals we see today. They were smaller, often irregular clumps of stars and gas forming from the gravitational collapse of primordial gas clouds. Astronomers, using powerful instruments like the Hubble Space Telescope, have been able to peer back in time, observing these nascent galaxies as they appeared billions of years ago. The Hubble Deep Field images, revolutionary in their time, captured faint, distant specks of light, each a young galaxy, revealing the universe's appearance when it was only a fraction of its current age. This observational triumph showed us the gradual assembly of galaxies, a process of hierarchical formation where smaller structures merged and grew, building up the larger galaxies we see today. Each merger was a cosmic dance of gas, dust, and stars, reshaping galactic forms and triggering new bursts of star formation, enriching the universe with the heavier elements forged within the first stars. Over billions of years, this process continued, with galaxies congregating into groups, then clusters, and eventually forming the vast filaments and voids of the cosmic web as gravity continued its relentless sculpting. The story of the universe's evolution from a fiery plasma to complex galaxies is a testament to the power of gravity and the fundamental laws of physics, unfolding patiently over unimaginable timescales. Every galaxy we observe, every star that twinkles, carries within it the echoes of this grand genesis, a lineage stretching back to the universe's very first moments. We are living in a cosmos that has already lived a long and eventful life. The patient work of cosmologists, astronomers, and physicists, from Lemaitre's bold hypothesis to Penzias and Wilson's accidental discovery, has allowed us to piece together this incredible cosmic memoir. We are not just observers of this story, we are a part of it. The elements within us were forged in stars, and those stars formed within galaxies that arose from the universe's initial conditions. Our existence is deeply woven into this grand narrative. As we reflect on the universe's past, from its genesis to the dawn of galaxies, a new question begins to form. If the universe has evolved so dramatically, what does its continuing journey hold? What future awaits this magnificent, expanding cosmos? That perhaps is a story for another quiet contemplation. Our previous journey concluded with the universe's grand evolution, from its fiery genesis to the dawn of countless galaxies. We saw how gravity sculpted matter and how stars forged the very elements that make up our world. But within this vast, dynamic cosmos, a more intimate question arises. Where, amidst this immensity, does life find a home? For life to emerge and then to thrive, it requires a delicate confluence of conditions. It is not enough to simply have matter and energy. They must be arranged in a very specific, sustained way. Scientists have spent decades quietly piecing together these requirements. The first essential ingredient is a stable energy source. On Earth, this is our sun, a star that has burned steadily for billions of years, providing a consistent flow of light and warmth. Erratic stars, prone to violent flares, would make sustained life far more challenging. Connected to this is the presence of heavier elements. As we learned, these are forged in the hearts of dying stars. Without carbon, oxygen, nitrogen, and iron, the building blocks of organic chemistry, the intricate molecules of life could not form. These elements, scattered by supernova, must then coalesce into planets, but not just any planet. The right kind of planet with the right conditions is a rare and precious outcome of cosmic evolution. Our sun, a G-type star, is not too massive to burn out quickly, nor too small to be dim and prone to intense flares. It sits in a sweet spot of stellar evolution, offering billions of years of consistent energy. The galactic neighborhood matters too. Our solar system resides in a quiet spiral arm of the Milky Way, far from the chaotic, radiation-filled center. This relative peace allows for long-term stability. The very elements in our bodies, the carbon and oxygen, are the legacy of stars that lived and died long before our sun was born. This cosmic recycling is fundamental to our existence. Without these heavier elements, planets would be mere spheres of hydrogen and helium, incapable of forming solid surfaces, oceans, or the complex chemistry required for life. The journey from stardust to complex life is a long one, requiring not just the right ingredients, but also the right environment to nurture them over cosmic timescales. Perhaps the most crucial requirement for life as we know it is liquid water. Water's unique properties as a solvent allow for the intricate chemical reactions that underpin all known biological processes. A planet needs to be at a temperature where water can exist in its liquid phase, neither perpetually frozen nor boiled away into space. This defines a very specific orbital range around a star. Beyond water, a protective atmosphere is vital. It shields the surface from harmful stellar radiation and meteoroid impacts, while also trapping enough heat to maintain stable temperatures. A planet's mass also plays a critical role. Too small and it cannot retain an atmosphere. Too large and it might become a gas giant, lacking a solid surface for life to take hold. Furthermore, a strong magnetic field is essential to deflect harmful solar winds, preventing the atmosphere from being stripped away over billions of years, a process Earth benefits from. These interdependent conditions led to the concept of the habitable zone, sometimes called the Goldilocks zone. It's the region around a star where conditions are just right for liquid water to exist on a planet's surface. This zone is not fixed, it shifts depending on the star's size and luminosity. A cooler, smaller star has a habitable zone much closer in, while a hotter, larger star's zone is further out. For many years, this concept was purely theoretical, an educated guess about where life might theoretically arise. The challenge was to find actual planets within these zones. The task seemed insurmountable, like searching for a single grain of sand on a distant beach. Detecting exoplanets, especially small, rocky ones, was at the very edge of our technological capabilities. But human ingenuity, driven by curiosity, finds a way. New methods, like observing the subtle dimming of a star as a planet passes in front of it, or detecting the star's wobble caused by a planet's gravity, began to emerge. Then came a revolution. Missions like NASA Kepler Space Telescope, launched in 2009, began staring intently at a single patch of sky, patiently watching for these tiny stellar winks. Kepler's findings were astounding. It discovered thousands of exoplanets, revealing that planets are not rare but incredibly common. Almost every star in our galaxy likely hosts at least one planet. Many of these newfound worlds were rocky, Earth-sized planets, and a significant number were found orbiting within their stars' habitable zones. The quiet universe suddenly seemed to whisper with potential. Following Kepler, the Transiting Exoplanet Survey Satellite, or TESS, took up the mantle, scanning nearly the entire sky for close-by exoplanets, adding even more candidates to our growing cosmic census. The initial excitement of discovery gave way to the meticulous work of characterization, determining a planet's size, mass, and orbital parameters. The search for life had moved from speculation to concrete targets. But finding a planet in the habitable zone is only the first step. The next, far more challenging task is to determine if any of these worlds harbor life. This is where the search for biosignatures begins. Biosignatures are gases or other phenomena in a planet's atmosphere that are strongly indicative of biological activity. On Earth, for example, the abundant oxygen in our atmosphere is a direct product of photosynthesis. Using powerful new telescopes like the James Webb Space Telescope, scientists can analyze the light that passes through an exoplanet's atmosphere, looking for these subtle chemical fingerprints. Detecting biosignatures is incredibly difficult. The signals are faint, and there are often non-biological processes that can mimic them, leading to careful, patient analysis and verification. The search continues, a quiet, persistent effort to sift through the cosmic noise for that unmistakable whisper of life beyond our home world. Every new data point brings us closer, or at least refines our understanding. Yet, despite the billions of galaxies and trillions of stars and the growing number of potentially habitable planets, a profound silence pervades the cosmos. This is the essence of the Fermi paradox. If life is common and intelligence a natural outcome of evolution, then where are the signs of other advanced civilizations? Why haven't we detected their signals or seen their grand projects across the stars? This paradox has many proposed explanations. Perhaps intelligent life is incredibly rare, or perhaps it doesn't last long enough to spread. Maybe we are looking in the wrong way or simply haven't looked long enough. The Great Filter hypothesis suggests there's a barrier to advanced life, either in our past, making life rare, or in our future, making it short-lived. The implications are both humbling and unsettling. The silence forces us to reflect on our own existence, making our presence here on Earth feel even more precious, a tiny spark of awareness in an otherwise silent, vast universe. Earth, it seems, is a unique outcome of a long chain of cosmic events. From the formation of heavy elements in ancient stars to our sun's stable longevity to the precise distance from our star, everything converged. Our planet's large moon stabilizes its axial tilt, leading to predictable seasons. Plate tectonics recycle nutrients and regulate climate. These are not universal features but specific conditions that nurtured life here. The abundance of liquid water, the protective atmosphere, the magnetic field, and a stable, quiet star all represent a delicate balance, a cosmic lottery won against incredible odds. Our existence, therefore, is not just a biological phenomenon but a profound astrophysical one. We are the conscious outcome of billions of years of cosmic evolution, a delicate miracle in the vastness. As we contemplate this delicate balance and our unique place within the grand cosmic tapestry, a new chapter of inquiry beckons. What future awaits this magnificent, expanding cosmos? And what will become of our tiny, precious home within it? That perhaps is a story for another quiet contemplation. Our last journey left us contemplating our delicate place within the vast, evolving cosmos. We learned of the cosmic web shaped by gravity and the mysterious dark matter. But the universe held one more profound secret, one that dictates its ultimate destiny. In the late 1990s, astronomers embarked on a meticulous task, measuring the universe's expansion rate. They used distant supernovae as standard candles, cosmic beacons whose intrinsic brightness was known, allowing their distance to be precisely calculated. The expectation was clear: gravity, the universe's great sculptor, should be slowing this expansion. Like a ball thrown upwards, it should eventually decelerate, perhaps even fall back. Yet the data from these supernovae told a startlingly different story. The universe was not slowing down. Instead, its expansion was accelerating, pushing galaxies apart at an ever-increasing pace. This unexpected discovery led to the concept of dark energy, a mysterious, repulsive force that permeates all of space. It's not a localized force, but a property of the vacuum itself, subtly increasing its influence as the universe grows. Dark energy now dominates the universe's energy budget, comprising about 68% of its total content. It is the unseen hand guiding the cosmos toward its distant future, dictating its ultimate fate. With this accelerating expansion, the universe's long-term future began to unfold in new theoretical models. The most likely scenario, given current observations, is known as the Big Freeze or heat death. Imagine a cosmos where galaxies, once clustered together, are slowly but inexorably pulled apart. The light from distant galaxies will become increasingly redshifted, eventually fading from view. Our own local group of galaxies, gravitationally bound, will remain intact. But beyond our immediate cosmic neighborhood, the accelerating expansion will create an insurmountable barrier, isolating us from the rest of the universe. Over quadrillions of years, the stellar nurseries will run out of gas and dust. New stars will cease to form. The existing stars will slowly burn through their fuel, one by one, fading into cosmic twilight. Massive stars will explode as supernova, leaving behind neutron stars and black holes. Smaller stars, like our Sun, will swell into red giants, then shrink to become faint, dense white dwarfs. These white dwarfs will slowly cool over unimaginable eons, eventually becoming black dwarfs, cold, dark remnants no longer emitting light or heat. They will be the cosmic embers of a bygone era. The universe will become a realm of darkness populated by these stellar corpses, black dwarfs, neutron stars, and black holes. The last light will flicker out, leaving only the memory of warmth. Even the mightiest black holes, once thought to be eternal, are predicted to slowly evaporate over truly staggering timescales through a process known as Hawking radiation. One by one, they will shrink and vanish, releasing their mass as a final, faint burst of energy. The grandest structures in the universe will dissolve, leaving nothing but a diffuse, cold gas of fundamental particles. If protons themselves are unstable, as some theories suggest, then over timescales far exceeding the age of the universe, even the atoms themselves might eventually decay, transforming into light particles and radiation. The universe will approach a state of maximum entropy, a uniform, cold expanse where no energy differences exist and no processes can occur. A cosmic equilibrium, silent and still. This heat death is not an apocalyptic event, but a slow, gentle fading, a gradual dissipation of all energy and structure. It is the ultimate triumph of thermodynamics on a cosmic scale. Other theories, though less favored by current data, once offered different fates. The Big Crunch hypothesized that gravity would eventually halt the expansion, pulling everything back into a singularity. And the Big Rip suggested that if dark energy continues to strengthen, it could eventually tear apart galaxies, stars, atoms, and even the very fabric of spacetime itself. But for now, the Big Freeze seems our destiny. This profound understanding of the universe's likely end can feel daunting, even melancholic. Yet, it also highlights the extraordinary privilege of our present moment. We exist in a universe still vibrant, still dynamic, where stars are born and galaxies collide. We are living in a fleeting, precious epoch of light and activity. Our ability to comprehend these vast timescales, to trace the universe's story from its fiery birth to its distant, cold end, is a testament to the power of human intellect and curiosity. Even in a universe destined for cold and darkness, the human quest for understanding shines brightly. It is a light that transcends the physical limitations of our existence. The beauty of cosmic processes, from the birth of a star to the evaporation of a black hole, remains constant, even if we are not there to witness every stage. Our privileged moment of awareness, our brief flicker of consciousness, allows us to observe, to question, and to construct this grand narrative of existence. The universe doesn't need us to be beautiful, but we are here now to appreciate its intricate dance, its vastness, and its quiet unfolding. The legacy of human curiosity and discovery is not bound by the lifespan of a star or the eventual chill of the cosmos. It is a timeless journey, passed from one generation to the next. We continue to observe, to wonder, to build instruments that peer ever deeper into space and time, driven by an unquenchable thirst to know. The scientific method itself, with its patient observation and rigorous testing, is a process designed to outlast any individual, any civilization, perhaps even any universe. It is a continuous dialogue with nature, a persistent whisper into the void, seeking answers to questions that have echoed since the dawn of human thought. From the infinitesimal dance of atoms to the grand sweep of galaxies, from the violent birth of stars to the slow, gentle fading of the cosmos, we have traced a story of interconnectedness. Our existence, our very composition, is woven into this cosmic fabric. We are children of the stars, born in a universe that is still young enough to hold warmth and light. The journey through the cosmos is not just an exploration of external space, but a profound introspection into our own origins and our place in the grand scheme of things. It teaches us humility in the face of immense scales and wonder at the intricate balance that allows for our brief, conscious existence. The universe's story is still being written, and while its ending may appear cold and distant, the chapters we are living now are vibrant with discovery. Each observation, each theory, each quiet moment of contemplation adds another brushstroke to this magnificent portrait of existence. The mystery continues to unfold. We are the sleepless scientists, forever peering into the darkness, seeking the faint whispers of truth, finding beauty even in the most distant, abstract corners of reality. And so, our gentle journey through the cosmos, from the smallest atom to the grandest galactic tapestry, concludes for now, leaving us with a sense of wonder that transcends time itself. The universe continues its silent, majestic dance, and we are but fleeting witnesses. As the moon climbs high, sleep well and carry the quiet echoes of eternity in your dreams.